Okay, so I haven't had time to write everything up, so I'm going to keep writing stuff up as we talk about it. So last time we started really going into integral calculus, which is the second major topic of this course, because there's differential calculus asking the question, how fast does something change? There's integral calculus asking how much is the total. And we saw a really simple example. If I take the line y equals x, and I ask for the area from x equals a to x equals b underneath this curve, well, that's really easy to find, because I can think of it as, if you like, a big triangle here, which has area 1/2 b squared, subtract a little triangle here, which has area 1/2 a squared, so we can find it really easy. Of course, nothing very hard, because these are triangles. Triangles are flat. And if you remember in the very first day of class, we said we love flat things. All right. Well, what if we don't have flat things? What's our idea? Well, our idea is we're going to just basically split stuff up into teeny pieces. Chop it up. So suppose I have my curve y equals f of x. And again, I want to go from a to b. Well, what am I going to do? I'm going to split a to b up into, basically, if you like, partition a to b into some points. But really what I'm going to do is I'm going to think of tiny little strips here. And I can say, well, each strip looks roughly more or less like a rectangle, especially when you get to really skinny strips, where the top of the rectangle, is relatively flat. And I can say, well, maybe it's not exactly a rectangle, but it's roughly a rectangle. What's the area of a rectangle that approximates this area? Well, I need a width. So the width of this rectangle, say, is delta xi, and I need a height. So I pick out a point of this interval, ci, and I plug it into the function. So this length here is f of ci. That's the height. So that the area of this rectangle is the function evaluated at some point in between the two endpoints here, defining this little rectangle, times the width. Okay. Now I have the area of one individual rectangle, which is approximately the area under here. What I do is I add up the area of each little rectangle that approximates each one of these areas, and that gives me a good approximation. And we call this a Riemann sum. So Riemann sum, we sum, say we have n intervals. There's some notation we learned last time where we have this sigma. Sigma means sum. Whenever you see a capital sigma, you say think sum. Here, the I is what we call a dummy variable, and it says we start summing at the index of 1. And we keep summing up till we get to n. So in other words, we do I equals 1, I equals 2, I equals 3, and we just keep going until we get to n, whatever n is. Usually n will be some number, but here's just a general formula. And then f of ci delta xi, that's the area of our ith rectangle. Now there's two special Riemann sums, which are called the right-hand sum, which we abbreviate r sub n. So r is for right-hand sum, n is for the number of intervals. And the idea of the right-hand sum is we're first off going to split all the strips into equally sized lengths. So instead of having the sizes vary on these rectangles, they're all going to have the exact same width. And we're going to call that width delta x. And that delta x is b minus a over n. So you take the length from b to a, divide by n. So equally sized n pieces. So that's part of it. The other part is that the right hand says we always add up the right endpoint. So for instance, if I come to my first interval here, which goes from a to a plus my delta x, would be my first point. Well, the right hand says for the first interval, choose the farthest right point you can. So in this case, a plus delta x. Then for your second interval, similarly, you choose the farthest right point you can, which would be a plus 2 delta x, and you keep going. And in general, you'll have the sum f of a plus I delta x. So this is a special case. The left-hand sum, very similar. But instead of using the right endpoints, we use the left endpoints. And so now, again, it looks almost the exact same. In fact, at first glance, it seems there's no difference between the two. The difference comes in our index. So here we started at 1, and we went to n. Here we start at 0, and we go up to n minus 1. Now, first off, we made some observations. And I should say that our goal last time was we were trying to figure out this question. Suppose I look at y equals x squared between 1 and 4. And I wanted to know how much area there was underneath that curve, y equals x squared between 1 and 4. Well, what we did is we chopped it up into 3 equally sized intervals, and we looked at the right-hand sums and the left-hand sums. So when you go through and you worked it out, we won't repeat it again. I'll just write these numbers down. The left-hand sum was 14. And so the left-hand sum, the rectangles we used were, for example, for the first interval, we would use this rectangle. For the second interval, we would use this rectangle. And for the third interval, we would use that rectangle. So here it's easy to see that the rectangles we used are in some sense too small because we're missing the area. In fact, we're missing these little pieces here. So this is an underestimate for the area from 1 to 4. Now when we did R3, the right-hand sum, we actually got a different number, which is good because it's a different kind of thing. We got 29. In R3, the idea is now we use the right endpoint. So for example, for the first rectangle, we'd use that one, and then for the second one, we'd use this one, and then for the third one, we'd use this one here. And now we actually have an overestimate. So we know that between 1 and 4, the area underneath the curve y equals x squared is somewhere between 14 and 29. Hopefully within the next 10 or 15 minutes, we'll be able to actually say exactly what the area is. Now, you notice I said something that here the L3 is an underestimate and the R3 was an overestimate. And in fact, that's something we wrote down. So let's write that down again, just so we remember it. So if our function f of x is increasing, then we have that the left-hand sum is an underestimate for the area, and the right-hand sum is an overestimate. Essentially, it's what we have in our picture. And the point being here is if our function is increasing, and if I just look at a typical rectangle, if I use the left-hand point, I'm way too low. And if I use the right-hand point, I'm, again, way too high. On the other hand, if f of x is decreasing, then it reverses. Rn is less than or equal to the area that we're after for is less than or equal to ln. Again, it's the same principle. If our function is decreasing, it looks something like this. And look at a typical rectangle. Now the right endpoint, right means the right-hand side. There we go. Right endpoint would use this rectangle, which is too low. We're missing area. But the left endpoint, which is over here, would use this area, which is rectangle, which is too big. Okay. Now there are some other things we mentioned. We talked a lot about sums. Sums obey some nice properties. And we're going to need some particular sums to be able to handle finding the area under the curve. So for instance, if I start with the sum j equals 1 to n of j. So this says what I do is I start at j equals 1, and then I just add the quantity j. So 1 plus 2 plus 3, and I keep going until I get to n. And this is n times n plus 1 over 2, or if you like, 1/2 n squared plus a half n. Now, I didn't get enough time to tell you the story last time. This is a very famous story you can look up because it's probably not true, but it's still a fun story. Carl Friedrich Gauss was a great mathematician, but when he was very young, he had a teacher who was having a bad day. So the teacher said, all right, I just want some quiet time by myself. So he told all the students, add up the numbers from 1 to 100. And so they took out their tablets, and they all started working, 1 plus 2, and then they kept track, 3 plus 3, 6, and they kept working on it. Young Gauss, he just sat there for a second, thinking. Finally, he took out his tablet, wrote down a single number, took it up to the front, put it on the desk, and put it down, face down. The teacher was very annoyed. He just guessed. At the very end, after all the other students had finished their work, the teacher pulled out Gauss's from the very bottom stack and looked at it, and he'd found the right answer. 5,050. Not only had he found the right answer, he was the only one who had the right answer. So what was the trick? Well, the trick was what I showed you last time, where you just add up in reverse. Then you just imagine adding up all the columns, n plus 1, plus n plus 1, plus n plus 1, plus n plus 1. And then you say, well, there's n of those. So the total is n times n plus 1, but I added it twice, so I need to divide by 2. So Gauss said, well, 1 to 100 is the same as taking 100 times 100 plus 1 divided by 2, which is 5,050. So it's a good story. So we have to tell it to keep the mythology alive. But that's not the one we're really going to need. We're going to need this one. Let's do the sum from j equals 1 to n of j squared, which is 1 squared plus 2 squared plus 3 squared, all the way up to n squared. Now, unfortunately, there's no neat trick. But this one has been studied quite extensively. And it's not hard to show that it's n times n plus 1 times 2n plus 1 divided by 6, which, if you multiply it out, that's 1/3 n cubed. And I want to make sure I get this right. 1/2 n squared plus 1/6 n. All right. Now I'm ready to attack a problem of this kind, y equals x squared. But instead of doing y equals x squared from 1 to 4, I'm going to do a sort of a more general case. I want to look at y equals x squared from 0 to b. So my goal is to find this area. So what I'm going to do is I'm going to look at the right-hand sum Rn and figure out what that would be. So Rn, by definition, that's the sum I equals 1 to n, f of, well, I'll just write down everything, f of a plus I delta x times delta x. Now let's start filling stuff in. Sum I equals 1 to n, f of a is 0, because I'm starting at 0, plus I delta x. OK, how big is delta x? Well, I'm chopping up from 0 to b into n strips. So the delta x would be b minus 0 over n, or if you like, b over n. So plus I times b over n times b over n. Now, of course, the 0 doesn't mean anything. So the function here, this is the function y equals x squared. So this is the sum I equals 1 to n of I squared b squared over n squared times b over n. So I squared b squared over n squared just came from squaring what's inside. And the b over n is from that delta x term. Now, notice that b squared over n squared times b over n does not depend on I. And our sum is indexed by I. So that means that really this is a constant. And one of the things that you can do is whenever you have a constant inside of a sum, you can pull it out. This is essentially factoring out a common term. So I'm going to pull it out in front. B cubed over n cubed times the sum I equals 1 to n of I squared. Now here, we did the sum j equals 1 to n of j squared. J is a dummy variable. So in other words, it's in there for the sum, but it doesn't really have any mean by itself. And so you don't have to use j. You can use anything you want. So for instance, instead of saying sum j equals 1 to n j squared, I could say sum I equals 1 to n of I squared. It's the exact same sum. I could say sum the smiley face. OK, that one did really well in the midterm. To n smiley face squared. So it's a dummy variable. So it's the exact basic sum that we have over here. And so what we have is we have b over n cubed times, and then I'm just going to copy what I have there, 1/3 n cubed plus 1/2 n squared plus 1/6 n. So all I did is I replaced what I knew this sum was, which is, moving it around, oh, whoops, sorry, I forgot this is a b cubed here, which is 1/3 b cubed is the first term when I multiply the first two together, plus 1/2 b cubed times 1 over n plus 1/6 b cubed times 1 over n squared. OK, so that's my right-hand sum if I chop it up into n intervals where n is some arbitrary number. Now, intuitively, if I want to get a better approximation, what should I do? Well, if you think about it, if I'm trying to approximate, if I use a fat rectangle, I'm going to run into trouble. Because if I use a fat rectangle, for instance, say I'm using my right-hand sum, then what I'm doing is I'm way overestimating. So these big, fat, wide rectangles are really bad. Okay, so what's the opposite of that? A skinny one. See, if I'm using a skinny rectangle, like this, sure, I'm off. Relatively speaking, my error is much smaller. Here I have a ton of error. Here I have much less error. And so that if I really want a better approximation, I really want n to be large. So what's the largest number we can think of? Well, infinity. Because there really is no largest number. So you just say, well, just keep getting big and bigger. So what happens as n goes to infinity? Well, this doesn't have anything attached to it. So it just stays 1/3 b cubed. This is a constant. What happens to the 1 over n? It goes to 0, because I'm having 1 divided by bigger and bigger numbers. What happens to this, where it's a constant times 1 over n squared? It goes to 0 as well. Because, again, it's 1 divided by something getting bigger and bigger. So as n goes to infinity, this part goes to 0. This part goes to 0. And you can think of it, if you like, these are the error of chopping it up. Because, we're overcounting. And essentially, this is saying roughly what we're overcounting by. So as n goes to infinity, this becomes 1/3 b cubed. Now, that's the right-hand sum. To be strict, I should also do the left-hand sum. But I'm not going to do that. I'm just going to state something, and we're not going to prove it. If our function f of x is continuous on the interval a, b, so a less than or equal to x, less than or equal to b, then if you look at the limit, I think maybe I've been watching too much curling or something. The Canadian commentators there are. Limit, okay. Limit as n goes to infinity of the right-hand sum is going to be the same as the limit as n goes to infinity of the left-hand sum. It's actually going to be the same as the limit of n goes to infinity of any Riemann sum, as long as the widths get small. So as long as your delta xi go to 0, then your limit of your right hand, limit of your left hand, whatever Riemann sum you want, as long as your smallest widths go to 0. Because remember, in our Riemann sum, your widths don't have to be the same. So you can do something really idiotic where you always have a big fat rectangle. Well, you don't want that. You always want to make sure you have skinnier and skinnier rectangles. So okay, so if your function is continuous, then these all match up, no matter what your function is. So in particular, we'll have that the limit of the left-hand sum is the limit of the right-hand sum. Now, why is that useful? Well, come over here. We're in this case. Our function is increasing. We have that our area is bounded above by Rn. So when the limit is bounded above by whatever the limit is, in this case it's 1/3 b cubed in the limit. Ln is going to be the exact same value. This is what this is saying. The limit of the right-hand sums is going to match the limit of the left-hand sum. So this is also going to be 1/3 b cubed. So what can we conclude about the area? 1/3 b cubed. What theorem are we using? Squeeze! You thought we would never see that again. Yeah, the area is getting squeezed in between. So now we know exactly what the area is. And in fact, we're ready to come back to this question. But not only will we answer this question, we're going to answer a much more general question. Namely, suppose I start with my y equals x squared, and I go from A to B. And I ask, what's this area? Well, what can we do? We can say, well, I'll take the area from 0 up to B, no problem. I know that area, 0, So the area from 0 to B that's 1/3 b cubed. And then what I'm going to do is I say, well, I really added too much to begin with. So I'm going to subtract the area from 0 to A, which is 1/3 a cubed. And lo and behold, we do that, we get 1/3 b cubed minus 1/3 a cubed. So that's the area underneath here. Very similar to what we did here. So coming over here for this special case, so this area is 1/3 times 4 cubed minus 1/3 times 1 cubed. Or if you like, stretch out to 1/3. 4 cubed is 64. 1 cubed is 1. 64 minus 1 is 63. Divided by 3 is 21. So in fact, the area is 21, which, as we suspected, is somewhere between 14 and 29. All right. So that only took us a lecture and a half to find the area between 1 and 4 of y equals x squared. Now, as you can imagine, we're going to get a lot faster at doing this, because we spent a lot of time trying to develop some basic ideas and tools of how do we get to this point. All right, let's see. Have we hit all the highlights of that section? Okay. All right. So coming back to this. So if I have a function which is continuous, I said that no matter what function you start with, if it's continuous on a to b, you look at left-hand sums, right-hand sums, Riemann sums, as long as your which are going small, doesn't matter, you're always going to get the exact same value. So instead of writing it out as this very complicated thing, instead of having to always write something like limit as your delta xi go to 0 of your sum I equals 1 to n f of ci delta xi, instead of always writing that down, which is your Riemann sum, we said, well, let's come up with some shorthand notation. So we're going to give ourselves some shorthand notation. So whenever these limits exist, which will be for continuous functions, which will be 99% of what we do, whenever the limits exist, we're going to call it a name. We're going to call it that. Now this we've seen before. We've seen something similar to this where we had antiderivatives. We called this the indefinite integral back then. Now you notice that now we have something slightly different. It's a twist. Whereas before, when we did antiderivatives, what were we expecting to get out? Well, we were expecting to get out a function. What do we expect to get out of here? A number, yeah, which we can interpret as an area, or we can interpret as other things. So, but here, we want a number out, and this is called the definite integral. And the key difference between an indefinite integral and a definite integral is you have these a's and b's. So these a's and b's indicate endpoints. So the way you can interpret this is you're saying, I'm trying to add up the function f of x dx from a to b. Now, if you think of it, you can sort of see things match up. For example, this f of ci matches with your f of x. Your delta xi matches up with your dx. Your sum was a sigma. Sigma started with an s. Stretch out the s. There you go. You got your integral sign, this is called the integral sign. And then the endpoint is a to b. And a to b, essentially, the idea is you have to know where to start and stop. And what you can do is you can actually go back and forth between these two. So one of the problems is you'll get something that looks like this. And you're going to say, well, rewrite it in terms of something that looks like this. So you'll get some practice doing that. So somebody said, how do we interpret this? Definitely one way to interpret this is area. I'm going to put area in quotation marks between x equals a and x equals b. Now, I put area in quotation marks for two reasons. One, we're going to use integrals to represent things other than area. So, for instance, at the very last thing we're going to do in this course are things called volumes. And we're going to do the exact same machinery. The idea behind integration is always the same. Split things up into tiny pieces, add up the result. Now, what you might get at the end is an area, but it doesn't have to be an area. It might be a volume. It might be a total of something. But it's just not area. So don't say, I don't understand. I thought we were trying to find volume, but integrals find area. No. It's just integration is always the idea. Chop into little pieces, add the pieces up. And in fact, once you have that idea in mind, it's really easy to understand how volume works, the volume formulas. And for things like arc length, which we don't do in this class. But once you understand, just chop into little pieces, add them up, everything falls in place really nice and neat. Now, the other reason I put area in quotation marks is we have a tendency to always think of area as being something positive, something that we can measure. But here, when I say area, I'm going to allow for the possibility of negative area. So in other words, if I have a function and it does something like this, and I start here at A and I end here at B, I mean, this is not, we know functions that do this. Things like sine and cosine, for example, do this. And I say, well, what's the definite integral from A to B of f of x dx? Well, the way that this is going to work is if I think about what's happening to the Riemann substance, I'm chopping into little pieces here. And if I look at one of these rectangles, it's going to say, well, it's approximately the height times the width. And so this is going to have positive values when I look at the little rectangles in here. So this is going to be positive area. Similarly, if I look at rectangles in here, again, same thing. This is going to be having positive area. But what about down here? Well, when I plug into my function is negative. So that in that part, if I look at this term, the f of ci is negative. My delta xi is positive. So that this area is actually negative. So I can have positive area, I can have negative area. And so that's why I like the area in quotation marks. So, for instance, suppose I ask you, what is the integral from 1 to 4 of x minus 3 dx? Well, I look at the picture. I know x minus 3 looks something like this, where 1 is over here and 4 is over here. And so I say, well, that's OK. What I can do is I can think of this as two triangles, a triangle over here and a triangle over here, where here it crosses at 3. So here the width is 2, the height is 2. So what's this area inside of here? 2 times a half. So a half base height would be 2, but because I'm below the axis, it's really going to be an area of negative 2. Now over here, I have an area of 1, a base of 1, a height of 1. So what's the area? A half. Wait. Yeah. 1 half times 1 times 1. Yeah, a half. So the area is positive when it's above the x-axis. So the total area is negative 2 plus a half, or if you like, negative 3 halves. Now, on the other hand, if I had asked something like, say, what's the integral from 1 to 4 absolute value of x minus 3 dx? Well, now my curve looks something like this. Here's 1, here's 3, here's 4. And now it's the exact same thing, except everything is now up above the x-axis. So this area is still 2. This area is still a half. Everything's above the x-axis. So the total area is 2 plus a half, which is 5 halves. So oftentimes you want to be careful. If a problem asks you for, say, the area between the curve and the axis, you have to sort of stop and make sure, well, how do I handle anything that's negative? And it's convenient to really let things be signed like this, have things which are positive and have things which are negative. All right. So let's go through and let's write down some basic facts. Things that we know already, things that we've figured out. Suppose I ask for the definite integral from a up to b of 1 dx. What would that be? So picture here, I have the line y equals 1. I go from a to b, and I want this area. So it's a rectangle. Base is b minus a. Height is 1. And so if this is finding the area, then the area is b minus a. If I want to do the definite integral from a to b of x times dx, Well, that's really what we did over here. Just finding the area from a to b of the function y equals x. So that's 1/2 b squared minus 1/2 a squared. We've also done the indefinite integral of a to b of x squared dx, which is what we spent our time working on at the beginning of class, 1/3 b cubed minus 1/3 a cubed. Okay, so those are easy. Let's write down some general facts about integrals. Things that we think should be true, and in fact are true. So first, suppose I ask about the integral from a to b of f of x plus g of x dx. So I'm trying to find the definite integral of these two functions added together. Well, intuitively, what should happen? Well, if it does anything like what we've learned in the past, it should say that's the integral from a to b of f of x dx plus the integral from a to b of g of x dx. And in fact, the intuitive thing is absolutely right. Now, how do we show this? Let me just run through a quick argument really fast how this works. What does an integral represent? It really represents slicing things up into little pieces and adding them up. So this I can think of as a limit of a Riemann sum. It's the sum I equals 1 to n of my function f of ci plus g of ci times my delta xi. That's what the definite integral represents. It's the limit of your sum. But what do we know about sums? Well, sums behave nicely. So first off, I'm going to just factor in. This is f of ci delta xi plus g of ci delta xi. And one of the things we did last time, I didn't write it on the board today because I didn't have time to write it up before class. If I have the sum of aj plus bj, I can do the two sums separately. In other words, I can break sums up into pieces. So that this is the limit, delta xi goes to 0, of my sum, I equals 1 to n, f of ci, delta xi, plus the sum, I equals 1 to n, g of ci, delta xi. Okay, so far so good. And now what I have is I have a limit of two things. I have a limit of this sum and I have a limit of that sum. What do we know we can do with limits? If I have a limit of two things added together, and I know what happens to each individual piece, then what I can do is just say that this is really the limit of the first piece plus the limit of the second piece. Which I'm fortunately running out of room. Okay, close enough. Okay, so what are we doing? We just broke the sum into pieces. Said the limit of two things added together is the limit of each individual piece. These are things we covered in essentially chapter 2. And then we say, aha, this is this integral, and this is that integral. And so we've made the loop. But it's just much shorter to say this. Now, you don't need to know this fact, but I just want to show you that there's reasons why things are true. And here, the reason things are true is you can break up sums, and limits behave nicely. Okay. So that's one fact. Let's write down another fact. If I have the integral from a to b of a constant k times my function f of x dx, what should we do with our constant? We should take it out. And again, this is one of the other things we did with limits. Sorry, not limits, sums. We did it earlier today where we said, well, look, we had the same thing in each individual sum. Remember the b cubed over n cubed. It's a constant with respect to sum, so I can move it outside the sum sign. Then I can move a constant outside the limit sign, and then I just have this fact. So this is not anything profound. We can use these two facts in conjunction with what we have here. Now we can find all sorts of integrals, namely anything which is just a quadratic equation. So if I want to find the integral from 2 to 3 of, say, 2x squared plus 3x minus 4 dx. Now it's very easy. What do? Is I use these facts. First off, I break up all the addition and say, instead of thinking of it as one big integral, break it up into 3 individual pieces. And at the same time, I pull out constants. So I'll do both things at once. So this is 2 integral 2 to 3 of x squared dx plus 3 integral 2 to 3 of x dx minus 4 integral 2 to 3 of 1 dx. And then I say, well, I know what this is. The integral of x squared from 2 to 3 is right here, except I put a equals 2, b equals 3. So that's 2 times 1/3 times 3 cubed minus 1/3 times 2 cubed. And that's that. Plus 3. And then I know the integral from a to b of x dx is a half b squared minus half a squared. So plus 3. So 1/2 b squared, so that's 1/2 3 squared, minus 1/2 a squared, so that's 1/2 2 squared. Finally, minus 4. Then the integral from 1 from 2 to 3 is 3 minus 2. And then I could just simplify if I chose the nice numbers, but of course I didn't because I was stupid. But there you go. We figured it out. All right, so these two facts say that integrals are essentially linear, a lot like what we said about derivatives and a lot like what we said about antiderivatives. So that's very good. So this should not be surprising. Now let's think about this fact. Suppose I ask to integrate a to a of your function f of x dx. What do you think we can say about that? It would be 0, yes. Someone said was wondering if it would be 0. Yes, it is absolutely 0. What's the intuition? Well, here's our intuition. I have a function y equals f of x, and I start at x equals a, and I go all the way until x equals a. How much area is there? There's no area. There's no width. Width is 0. So yes, so the area of that is 0, so the integral is 0. All right, now the tricky one. Suppose I ask the integral from a to b of f of x dx, and I want to compare it to the integral b to a of f of x dx. Now, I'm not saying whether a is less than b or b is less than a. It doesn't really matter. What's the relationship between these two? Now, this one is a little bit tricky, so I'll just tell you. They're almost the same, except they differ in the sign. So in other words, if you have a definite integral and you swap the signs, swap the order that you're integrating from, you have to swap the sign. So for instance, the integral from 3 to 0 of x dx, well, I'm not used to the 3 to 0. That's kind of weird, so I'm just going to swap it. So that's negative the integral of 0 to 3 of x dx. And then, now I feel much more comfortable. 1/2 times 3 squared minus 1/2 times 0 squared, or negative 9/2. Now, why do we change the sign? Well, you might say, well, I don't remember us having anything to do with sign. And let me point out where it is. The reason that we're going to change the sign when we reverse the order is because of this guy right here. Because what happens when is you chop up from a to b, well, if I go from a to b and I chop it up this way, well, really, I say I start at a, and then I move over, and then here's my width from where I end from subtract where I start. What are my widths? They're positive. But if I go backwards, a, b, so that says I start here and I move in this direction. So I take this value minus this value for my width. That's a negative value. So the delta xi becomes negative. That's why we switch the sign. This stays the same. This changes sign. So that's why we change the sign. One more fact, and then we're done for the day. So the last fact for the day, this is a nice fact. It says, suppose I want to look at the integral from a to b of f of x dx, and I also have the integral from b to c of f of x dx. So I have these two integrals. The this says you go from A to B, and then wherever B is, you go from B to C. Well, it seems fairly reasonable that, well, if I'm going from A to B, then I go from B to C, that should be the same as going from just A to C. And it is. So in other words, A to B plus B to C is the same as A to C. And that's what we used here, where we said the integral from A to B is the same as the integral from 0 to B minus the integral from 0 to A. All right, have a good day. See you on Wednesday. Woo! Unless you come to my office hour.